Okay, all right. The other section will be happy. So let's do a quick recap of our postulates so far. The first one was the wave function. All right, and which is just, again, any particle, any system can be represented by a wave function. All right, it's just that we saw it in problem set 1. Our wave functions were our little vectors, our little color vectors. All right, we're really going to be dealing a lot with functions here. We'll talk about why. I've kind of mentioned that already, about why we switch between functions and vectors. But every system has a wave function associated with it, and everything that we want to learn about our system is encoded in that wave function. The wave function determines all the properties. So every physical system so whether it be an electron, a hydrogen atom, a molecule, your body, doesn't matter, anything, the universe has, you could say, has a wave function even. Every physical system has a wave function. All right, and the notation that I give you for wave function is psi, it's a Greek letter. And in our case, we're going to be thinking about it in terms of position and time, r and t, right? R is a vector in whatever space we choose. It could be 1-dimensional, 2, or 3. And of course, we might want to think about time later too. So we'll just keep time in there. And the wave function satisfies a couple of properties. So what are the properties of the wave function? So first of all, psi has to be, this is kind of a side effect. Psi has to be a smooth and continuous function, which means that it doesn't have any discontinuities, and it also is differentiable. Smooth means that it doesn't have any jerks in it, right? So the derivative is defined at all positions. What this means is that the derivative of psi with respect to x exists. Actually, all of its derivatives exist. The first, the second, the third, the fourth, and so on, but that's okay. We don't have to worry about that so much. But it's just a smooth function, so it can't just be like a step function. You know, it can't be things like that. It has to integrate, and it has to have a derivative. All right, the next property is that psi may be complex valued, right? It might output complex numbers. Doesn't have to. We'll see in our toy model that we're going to talk about the particle in a box, we won't have to worry about i's because we'll be able to set it to a real solution. But in general, it might have complex numbers. And the most important property of the wave function is the Born approximation, or the Born interpretation. Right? This is the big thing that this is kind of the foundational property of the wave function, the thing that we actually care about as someone who measures a system, how we measure an electron, how we look at things, is that the value, when we take the wave function and we square it, and we put it in a small volume dx, dy, dz, this is the probability of observing the system. Sorry, that's observing. In the volume dv, which is dx, dy, and dz. Okay, so we have a big box. We put our electron in there, and we want to know what the probability of finding that electron is in a tiny little portion of the box. All we have to do is evaluate psi squared inside of that box. And the conclusion of this, which is that if we take the integral and we integrate it over the entire space of our region, right? So if we integrate over the entire box, integrate over the whole space of psi squared, dx, dy, dz, this is asking what's the probability of finding the particle in the entire box. Right? We're summing up all the little chunks, dx, dy, dz, all the little volumes into one big volume. So this is the total probability of finding the particle or the system in any place in the box, which of course there's a 100% chance of that because it's in the box, right? And so this integral always has to equal 1. Right? This is a 1, not a 2. 1. Okay. Right. This is just implying that the probability of finding a particle anywhere is 100%, or the chances. Right? The probability is 1. Or probability runs between 0 and 1. Okay. This is all we need to know about the wave function right now. It's got to be smooth and continuous. It may be complex valued, and that the square of the integral has to be equal to 1. Right? This is again the same. These are the same statements that we made about vectors in probable set 1. Psi is, of course, vectors aren't smooth and continuous. They're vectors, but remember we showed that the state of the electron can be any combination of black and white. So it's a smooth and continuous function of that space. Right? It can be any vector along the unit circle in the black-white space. It's obviously, well, we didn't see this for color, but it is complex valued. We've just gotten rid of the complex numbers, but there's complex numbers hiding in there. And we showed that the length of the vectors have to be 1. And how do you calculate the length of the vector? You square it. Square the vector, right? You take the dot product of itself. You take the dot product of the vector in of itself, which is psi squared, and you get the length 1. Right? So we have functions that integrate to 1, what we call probability functions, right? This tells you something about the probability. It has to integrate to 1, just like the vectors have to have length 1. Same concept. But now we're dealing with a space that's continuous. Right? X, Y, and Z can be any value in our space, continuous variables. Whereas with the electron, it can only have 2 possibilities. It can either be black or white. Right? Here, the electron can be in any position in the box. Right? There's an infinite number of places it can be. So, which is why we move from vectors to integrals, to functions. Because it's much easier to integrate a function than it is to measure or to manipulate an infinite length vector, which would be the equivalent here. Okay, so that's all we need to know about the wave function right? Again, there's no specification for what it looks like yet, but we'll be able to come up with an equation, a formula, if you will, that allow us to solve for the wave functions of our system. We'll be able to come up with them. All right? We'll have to specify our system. What are we putting the electron in? And then an equation will allow us to find the valid wave functions that are associated with that system. And they'll satisfy all of these properties. Okay, so that was the first one. And the second one, we'll just do a little shorter, was this idea of linear operators. All right, let's just remind ourselves what that means. It says that any measurement to any measurement, there corresponds, let me say a measurement more specifically, a measurement of a physical parameter or a physical observable, right? That's energy, position, color, flavor, you name it. Anything that you can measure on your instrument. There corresponds a linear operator that satisfies the following properties. I'm going to give the operator a name real quick, sorry. It's just so we have it. So I'm going to write the general operator O, and I'm going to put this little caret hat on top of it. All right, anytime you see that, think operator. All right, so this is a generic operator. All right, and that satisfies the following properties. Okay, so here's what the property is for a linear operator.
What does it say after of a physical property? Is that supposed to be that corresponds?
Oh, okay. To any measurement of physical observable, there corresponds. Thank you. There corresponds a linear operator, which we call O, that satisfies the following properties. All right, so let's make some assumptions. assume that when we take O and we measure a wave function psi1, we get a number back, O1, times the original wave function. All right, this is just like when we measure color, right? We got when you measure color of a white electron, you get a 1 back. That's your O, your little number. If you measure a black electron, you get a -1. That's your little O for it. All right, we call those eigenvalues. We'll talk more about that in a second. And let's make one more assumption, that when you apply O to a different wave function, and let's just say you get a different number, like that, then when you take the operator and apply it to the sum of these two states, all right, so this is like measuring, so if psi1 is white, psi2 is black, now we're going to measure something that's black and white together. This is the same as taking the operator for psi1 plus the operator to psi2, which of course gives us O1 psi1 plus O2 psi2. All right, this is just a distributive property. Right, this is just a distributive property. Right, you've seen this in math, right? This is just like if you take A times B plus C, you get AB plus AC, right? Distributive property. So this seems really trivial, but it's not. This is actually very important. I kind of explained that last class. Is that Newton's physics, for instance, are not linear in this way. They're not distributive. Right? So there's actual classical physics with multiple bodies, 2 particles or 3 particles that are all represented by some trajectories. Measuring their trajectories is not, they're coupled together, so they're not independent of each other. You're going to have some combination where one trajectory affects the other. That's why we have the 3-body problem. That's why it's so complicated to measure orbits of things, complicated systems of orbits, like the solar system, because all of the planets and all the suns and stuff, they're all interacting with each other, right? Like the Jupiter's motion, for instance, affects Neptune's motion. And actually the big planets, actually Mercury's motion, for instance, is incredibly affected by all the other planets as well. They're all coupled together. But in quantum mechanics, we don't have that problem. In quantum mechanics, we can always just distribute things, right? We can treat the physics of 2 bodies as the sum of physics of 2 one-bodies. Okay? Really, really important characteristic. This is what's called linearity. You know it as your algebra teacher called it the distributive property, but I'm going to call it linearity. Because this is what lines do. Linear functions do this. Linearity. That's why we call them linear operators. Okay? I gave you a big long list at the end of last class, different operators. Talked about position and momentum and energy. Gave you a bunch of big long lists, and we saw that they were, X was the X operator is just X. But the energy operator, had a second derivative in it and stuff. There's, complicated operators, but they're all linear. Okay, so they all satisfy this property. Just like you probably saw in problem set 1, color and flavor. We saw for color is also a linear operator. It works exactly like this. Okay, so this gives us 2 things. First, it gives us a system, right? Our wave function. That's how we represent our system. And then our operators represent our measurements, right? They're the things that the legitimate actions that we can do on our system. All right? I want to continue this idea to give us the third postulate. And the third postulate is very much related to operators. Okay, so here I've defined this measurement device. These are our boxes in problem set 1, color and flavor or whatever. And they have these properties that they're linear. I want to look at a very specific class of operators and results that will ultimately satisfy, right? We got to think about, as you saw, for instance, in problem set 1, you can throw anything into a flavor box or a color box, but it doesn't mean you get a valid measurement out. You can put anything you want through a flavor box, but it doesn't mean that the thing you get out at the end is the same as the thing you put in, which is what we have here. Right? I put in my psi1 as an input and I get psi1 out. I haven't changed my state. We saw that there are states that you put in, you get different ones out. Nothing wrong with that. But we should focus in on I want to focus in on this property here. This set of functions that when I put them, or set of states, that when I put them in the operator, I get the same state out. Okay? There's any number of functions I can define that change when I put it in. Right? Where psi1 you get a different one out. It's an infinite number of those. Right? I'm more interested in the ones where they don't change. Right? Where the operator leaves them unchanged. And these turn out to be the things that we actually measure in our experiment. Our system is represented by the states that don't change with regard to our measurement. Right? These are the system, the actual states, physical states of the system. Okay, so what I'm going to write, our third postulate, many different names. I'm just going to call it very generally, this is the eigenvalue postulate. Now, I've used this word before on the homework and in class, and now I want to talk to you very briefly about what an eigenvalue is. Just talk about the definition of it. We're not going to go too deep into it because you guys haven't taken linear algebra. I'm going to try to slowly introduce these concepts to you, but let's just talk about them very generally without having to do too much math. Okay. So here's what eigenvalue, not position, sorry. I meant to write postulate there. So I'm just going to call eigenvalues instead. And let me save this in case it crashes. All right, so my postulate is this. In any measurement of the physical observable corresponding to operator O, all right, that could be color, energy, position, whatever. The only values I will read out that will ever be observed are let me write it in a different color, eigenvalues and there are a set of numbers which we'll call A sub n that satisfy the following equation. Now there may be one that satisfies this equation. There may be an infinite number. Don't know. Depends on the system. All right, and the equation is this. When we take O and we apply it to some wave function psi sub n, all right, there might be n of them. Right? For instance, in color we have two. There's black and white. Let me change that. Yeah, A sub n psi n. All right. So here's the big take-home point. Is that we can come up with any operator we want. We can measure anything as long as it's linear, it satisfies some properties that operators satisfy. I haven't specified all the properties it has to satisfy. That's not important. So far, I've only talked about operators that are real. Right? This represents some physical measurement. This is my system. Right? Here's my electron going into my O box. And the only valid responses, the only valid measurements I'll ever get out of O, the box O, are the eigenvalues for all of the functions where when I put them in, I get the same one out. Okay? So the idea is that if this is a measurement of my system, here's my system, the only things I will ever observe in my experiment are the states that when I put them through the box, I get the same state out times a number. All right, and a number is what we call the eigenvalue. Right, this is just the quantum measurement theorem from problem set 1. Now I've given it a different name because in homework 1. Same idea, right? The only valid physical measurements of something is that when I put my electron into it, or my state into it, I get the same electron out, times a number. And the number is my measurement of that object. So for instance, again, if my electron is white, and this is my color measurement, I get the white eigenvalue out, which is +1, and a white electron. If I put a black electron in for color, I get a -1 out. That's what my measurement is, -1. That represents black, and I get the black electron out. Okay. This is always satisfied for any state that is defined for this property. Right? So for instance, what about energy? Right? Imagine that we have a hydrogen atom. Imagine our wave function represents a hydrogen atom, and we want to measure the energy of that atom. Well, all a hydrogen atom is really is an electron orbiting a stationary proton. That's the way we're going to define it. So the wave function for hydrogen actually represents the motion of the electron. The proton in the middle is not moving. Right? So it's really just the electron. Right? So the electron can be in multiple states, right? It could be in the 1s orbital, it could be in the 2s, the 3s, the p's, the d's, right? You've learned all these orbitals. Each one of these orbitals corresponds to some wave function. And so when I put my electron in, or my hydrogen atom into my energy box, and I measure the energy of it, well, if the particle is in a 1s state, I'll get an energy out that's corresponding to the energy of the 1s state. That's my eigenvalue. If it's in the 2s state, I'll get a different number out here, and that would be the energy of the 2s state. Okay? I might not know what state my electron's in, but I'm guaranteed that when I put it through the box, I'm going to get one of the results. All right? It could be the 1s, it could be the 2s, the 2p, who knows? Right? Depends on the system. But the fact of the matter is I'm always going to get one of them. Right? The hydrogen atom is always going to be 1s, 2s, 2p, 2d, 3d, all of those states. Nothing in between. Right? There's no half state between 1s and 2s. There's only 1s and 2s. So if the electron can only be in the 1s or the 2s state, and I put it through the energy box, I'm either going to get the energy of the 1s state or the energy of the 2s state, and nothing else. Those are the only possible results. And we're going to see that today. Very, very clearly. Because I want to follow this up with a corollary, we're going to call this 3b, just an application of the postulate. And this is what's called the Schrodinger equation. This will be our big tool in this class. Erwin Schrodinger, physicist from Switzerland, 1910s, very strange man. But he came up with a beautifully simple equation which says that he writes it like this, that the operator H, which is total energy, the Hamiltonian, I introduced that to you last time, I'll talk about it again, applied to a wave function for any state, psi n, returns the energy of that state times psi n. Right? So often you'll see this written as H psi is equal to E psi. Right? This is the Schrodinger equation. Right? And it's literally this statement. Right? It says that for a system, say a hydrogen atom, when I apply the Hamiltonian to the hydrogen atom, I get a hydrogen atom out in some state of the hydrogen atom, 1s, 2s, and I also get its energy, 1s, 2s, and so on. Okay. So the nice thing about this is, as we'll see in a second, this is an algebraic equation we can solve. So if we can define what H is, we can write out what the Hamiltonian, the energy operator is for a system. That's what we're going to do today. And we know that it returns when you apply H to a function, it returns that function times a number, which is the energy in this case. Right? So if we know what H looks like, E is just a number, it's just a constant. We have an algebraic equation here. It says when H is applied to a function, it gives the same function back times a constant. Right? We can solve this. assuming that H is well behaved, right? Assuming we have something that isn't crazy for H. So let's look at that today. So what is H? Now I wrote it down in my big table, but I didn't really contextualize it too much last class, and I'll rewrite it for you. So let's look at the Schrodinger equation a bit. H psi is equal to E psi. And I like to write it like this. I'll put a little hat on it. So what is H? Well, as I said on last class, H is called the Hamiltonian. That's our friendly name for it. And it's the total energy of the system. And our total energy is the sum of kinetic plus potential. So H is equal to the kinetic energy operator, T, plus the potential energy operator. Right? This is kinetic and potential energy. I talked a little bit about the forms of these two operators, the kinetic and the potential. We know what the kinetic energy looks like. It looks like 1/2 mv squared. But the problem is that using velocity isn't very helpful because velocity is not conserved. So instead we use momentum. Momentum is conserved. So we always want to keep things conserved. Space is conserved, translation is conserved, so x is a good variable. Energy obviously is conserved. That's the first law of thermodynamics. And momentum also is conserved. So we typically represent things in these positions. We position momentum and energy. These are things that are always conserved in physics. So we're going to write that instead, the kinetic energy, as the operator momentum squared over 2m. It's not hard to show if you let P equals mv, right? That's the definition of momentum for a classical particle. It's not hard to show that 1/2 mv squared is P squared over 2m, just a little bit of algebra. And our potential energy it depends on the system, right? The potential is going to determine how the particle interacts in the space. So for instance, if it's affected by gravitation, it feels the force of gravity, we're going to have a potential energy that corresponds to its height relative to the floor, right? mgh, right? That's what we talk about, gravitational potential. Maybe, for instance, in the hydrogen atom, the electron is attracted to the proton through electrostatic interactions, electromagnetism. And that potential goes as 1 over the distance between the proton and electron, 1 over r. Right? So our potential for the hydrogen atom will look something like 1 over r, 1 over x. And then when we talk about bonds and springs, that potential is x squared. It's distance squared. Right? So the potential determines the shape of the system. Right? It tells you something about the geometry of where you're placing your particle. Right? So it changes. So it's just a function, though. It's a function of position. So it's a function of x, y, and z, if it's in 3 dimensions. Okay, and I'm just going to, now we have to evaluate p squared. We go back to our table, recall that the p operator is minus I h over 2 pi times the derivative with respect to position. Okay, so when we evaluate the idea is when we evaluate the momentum of a wave function, the momentum of a particle, we have to take the derivative of the wave function. So we've got to take the derivative. So let's square it now and simplify this a little bit. This means that h is equal to, well, let's factor out some numbers. We have an h over 2, we have an I, well, let's leave the I in. We have a minus sign. Actually, no, sorry. Let me just put this all in. So this is 1 over 2m minus IH bar h over 2 pi d by dx squared plus v of x. I'm just going to do one dimension. but we can write x, y, z if we wanted. And so let's do this math a little bit. We get a factor of, so the minus sign cancels out, but we have an I squared that gives me a minus sign. So we have a net minus sign here. We have an h squared in the numerator. And then we have 2m times 2 pi squared, so that's going to be 8 pi squared times the mass of the particle m. And then we have the derivative squared, which is just the second derivative of the function. It's derivative of the derivative plus v of x. All right, so let me write that in big words. I'm going to do one more simplification. This is a very important one. I'm going to write this in a big box for you. We're just going to put some constants together. Right? I have this pi squared. It's really ugly. I hate. We're always going to be dealing with a lot of pi's in this class because we're complex, so things are moving in a circle. So there's going to be pi's everywhere. And so I'm going to introduce a simplification called the reduced Planck constant. And I'm going to take, it's going to be called h bar, as it's an h with this little bar through it. And everyone calls it h bar, okay? No one ever calls it the reduced constant. Everyone calls it h bar. And this is the Planck's constant h divided by 2 pi, okay? So the reason why I introduce this is because when you look in the textbook and you look at when we get to later problems, we're going to see h bar a lot. Because there's going to be these factors of 2 pi from everywhere because of the complex plane. There's all these factors of 2 pi and angle and stuff, and I just want to get rid of them. I don't want to think about them. So I'm going to make a new constant, which is h divided by 2 pi. H is around 6.6 times 10 to the minus 34. 2 pi is around 6, 6.1, 6.2. So this number is around 1 times 10 to the minus 36. All right, it's just a number. You can look it up. Literally, if you type h bar in Google, it'll give you a value for it. All right, this is a real bona fide constant. All right, again, it's related to another one, but we use h bar almost as much as we use h. Okay, so just remember that they're off by a factor of 2 pi. The reason why we use this, again, remember it has something to do with, remember everything's moving in a complex plane in a circle. We saw that originally with the wave function, and so this 2 pi has something to do with angular frequency. All right, it's how fast it moves per radian instead of over the entire circle. All right, so it's a useful number, and it comes up a lot. So we can rewrite now our Hamiltonian operator in its classic form, which is minus h bar squared over 2m times the second derivative of position plus my potential, which is system dependent. Okay, every problem that we do in this class, we're going to come up with a model, right? We're going to think about bonds, we're going to think about hydrogen atoms, whatever. We're always, I'm sorry to block the screen. We're always going to write this down first. Right? We're always going to have this kinetic energy term. This is the kinetic energy of any particle, anything moving. And we're going to have to come up with a potential function that represents our system. Right? So this is kind of our first step to everything, right? Operationally, when we want to figure out how a system behaves, we're going to write down the Hamiltonian, and we're going to solve the Schrodinger equation using the Hamiltonian that we come up with. All right? You'll see all this work together in about 10 minutes. Okay? We've got a bunch of different weird things going on here. Right? And so operationally and mathematically, it's not clear what's going on immediately. But let's set up a problem and try to solve this, right? We know that when we apply this function here, this operator, which is a second derivative and some function, to a wave function, we get the energy times the wave function back. Right? Those are the possible states of our system, those wave functions. So we have an equation here that relates the wave function to itself. Says that the second derivative of the wave function plus this function of x times the wave function should give me the wave function back times a number. That's Schrodinger's equation. Right? So we have to find the wave functions that satisfy this property. All right, so we're going to put this into, right, we're going to solve now h applied to a wave function is equal to e times that wave function. All right, so let's work this out explicitly for a very simple problem. Now, it is very simple, the problem we're going to be doing, but actually it's very powerful, and it's very instructive, and it teaches us everything we need to know about quantum mechanics. Right? We'll be able to apply all the postulates to the system and start thinking about it. And the best part about it is that we can apply the system to chemistry. Right? It'll have a very natural application. And in fact, I think, oh no, the problem set doesn't. I got rid of, there was a question that related this model that we're going to talk about to chemistry, but I think we'll do it in class instead. Okay, so let's introduce this toy box, this toy model that I want to do with our first three postulates. It's called the particle in the box model. If you've ever talked to Abby here up in front, who's loitering in my class, she probably tells you that she has some unresolved trauma about the particle in a box, but that's only because I'm very enthusiastic about it and I'm a big fan of the model, and so you'll see it a lot in this class, probably till you get sick of it. But the really nice thing about this system, it's very, very straightforward, and it teaches us everything we need to know about quantum mechanics, for the most part. So here's what the system is. All right, I'm going to take a particle. All right, so my setup for my experiment. I'm going to take a particle. Bless you. And I'm just going to say for now, let's just do an electron because that's what we've been looking at. Electrons are nice because they don't have any size. They have a mass, but they don't have a shape. Okay. So we have an electron E minus that has, let me just write down the mass of the electron because you'll need this eventually. And you can look it up later. 9.109. 384 times 10 to the minus 31 kilograms. All right, this is the mass of the electron, roughly. There's more digits, but I'm not going to write them. All right, when you see m sub e, that means the mass of the electron. All right, we're going to take this particle and we're going to put it in a box, put it in a 1D box. What is a 1D box? It's a line. This is effectively on a line with infinitely high walls on the edges. Okay, so let me draw this on a coordinate system for you, just to get a sense of what the system looks like. My x coordinate. All right, and we're going to make the box a finite length. Okay, so I'm going to draw my box. Like that. Let's define it. Yeah, that's fine. We'll define it so that this runs from, sorry. This box runs from x equals L minus L over 2 to L over 2. No, that's not a very good way to write this. I'm sorry. So let's say the box runs from 0 to L. All right, so the left-hand side of the box is at x equals 0, and the right-hand side of the box is at x equals L. So it's a box of length L. All right, and the electron can exist inside this box. Anywhere in the box, right? So I'm going to put it right here. Here's my electron. All right, it's a one-dimensional box, so there's no vertical direction. It's just on the line.
Is that supposed to be a 0 or
here?
Yeah.
Yeah, it runs from 0 to L.
Oh.
Yeah, I've drawn this poorly because it should be right here on the axis, but that's okay. Not a big deal. So we're going to put this electron here, and then it can exist anywhere between 0 and L. Well, it can't exist at 0 and L because those are the walls, but any value between them, it can exist. And so, but the point is that it can't exist outside the walls, right? Basically, once it's in here on this line, it's trapped. So these walls are impermeable. All right, and the electron only exists between 0 and L. Okay. So remember that what I want to do, the only thing I have to do, I already have an equation for the kinetic energy of this electron. I have to come up with the potential. What's the potential of this electron? So remember, the potential is a function of position. So we need to ask, what's the potential energy of the electron in the box versus outside of the box? Right? What's the value of that potential? So we have a potential function v of x, and it has two values. So when it's inside, when the electron's inside the box, the electron's able to move freely. It says that there's nothing there. Right? The electron just exists in a vacuum on this line. All right, so within the box, there's no preference energetically to be on one side of the box or the other. It's all the same. All right, so there's no potential energy. All right, so when the electron is in the box, but when it's between, sorry, let me write that, not greater than or equal, but in between the 0 and L, the potential is 0. It's a free electron. No repulsion, there's no attraction, there's nothing. It's just free to move. And of course, what's the potential on the outside of the box? Well, it can't escape. It has infinitely high walls. So the potential outside the box is infinite, right? It has to have infinite energy to be outside the box. It's infinitely hard to get outside the box. Right? So this potential is infinite outside. So x is less than or equal to 0, or x is greater than or equal to L. It's infinite. Okay, so what we've done basically is we've taken a free electron floating freely in a vacuum in space, and we've put some walls there that it can't move, it has to move between. Okay? Can't go past them. And so we've basically taken a room. This is like the box here is a finite room, if you will. Right? Instead of having the electron exist in an entire universal, like infinite vacuum, we've contained it into a single room, which is our box. Okay? Now this is very nice for potential energy, because in the region where the electron exists, the potential energy is 0. So there's no potential energy. We don't have to worry about that function. All right, so let's now, we have everything we need to know about the physics of this system. We're going to apply the Schrodinger equation. So now we're going to apply Schrodinger. Which says that H psi is equal to E psi. I'm going to write little n's here. Well, let's not write any n's yet. Let's save the n's for later. We actually don't know what the wave function looks like yet. There might be many, there might be one, we don't know. And so let's work out the operator for this. So this is minus h bar squared over 2m d squared dx squared. Now I'm going to put the wave, I'm going to apply it to the wave function. So when we apply it to the wave function, we're taking the second derivative of the wave function with respect to position. Remember, we're only going to look inside the box. Outside the box, the energy is infinite, so we don't have to consider it. And we know that when we apply this derivative to the wave function by Schrodinger equation, we get the original function back times a number, e. Okay. So we have what's called a differential equation here. All right, we have some numbers here. Okay. We can arrange this a little bit, but if you think about it just a bit, what does this equation look like? All right, so imagine E is 1, and we can ignore this number over here. Okay, just a second. They're just constants. All right, so if we ignore the constants on this term, what we have is that the wave function satisfies the property that when you take the second derivative of it, you get the original function back. Okay, so the only valid solutions to this equation are functions whose second derivative is the same as the function. Well, that really limits our chances, or what do you call them? Our choices, right? Because imagine if psi is x squared. Let's just guess a quadratic, right? That's a classic problem. When you take the second derivative of a quadratic equation, x squared, you get a number, right? X squared, first derivative of x squared is 2x. Derivative of 2x is 2. That's not the same function, all right? So it can't be a polynomial. Does anyone know any functions whose second derivative is the same as the original function? You can think about it a little bit and yell out if you have an idea. What's a function that we can take the derivative twice and get the same function back? You've seen it before. Guarantee you've seen it before. Not just in this class, but most math classes. Yeah, go ahead, Damien.
A sine equation?
Absolutely, a sine equation. So here's an option. Sine of x. Let's say sine of kx. We don't know what the coefficient is. What's another one? Same argument. If not sine, it could be, yeah, cosine. Cosine does the same thing. Does anyone have any other ideas? E to the x. All right, so we have three options. There's one more. I'm just going to write it, and we're not going to worry about it, but e to the ikx is also a function. But remember, e to the ix is just sine and cosine with an imaginary number. So this is still sines and cosines. So we have a choice here, sine kx, cosine of kx, and e to the x. What was the other property we need to have for our wave function? What's the number one property of our wave function it has to satisfy? I heard that. Go up.
Continuous and smooth.
I'll say it again.
Continuous and smooth.
Well, they're all continuous and smooth. What's the other one though? The big one, the Born interpretation. What was that? And the integral has to equal 1 over all space. Well, if you integrate e to the x from 0 to infinity, for instance, it's not going to be convergent, right? It diverges. It's not a very good function to choose, right? Because it diverges. It goes exponential. Okay? So e to the x probably isn't going to work for us. Because e to the x doesn't satisfy the property that the square of it gives you an integral of 1 over all space. However, so let's look at cosine and so that kind of limits us now to either e to the ikx, which is just an imaginary cosine sine function, or we could do the real ones. So let's do the real ones. These seem to satisfy all our properties so far. So let's try this one. So in fact, that's exactly the right answer. So the general solution so it can be either cosine or sine, but the wave function solution is a, let me just make sure I have my labels correct here, just a sec, guys. Yeah, okay, sorry. Cosine kx plus b sine kx. Okay. Now, a and b are numbers we have to determine. And I'll just write here that k actually just comes out of the equation. K here is the square root of 2 times the mass of the electron times its energy over h bar squared, h bar. All right, that's k. So the frequency of the wave that's associated with this electron and some energy is a wave with frequency that's proportional to the square root of the energy. All right? Once again, remember we have waves, right? Particles are waves and particles at the same time in the superposition quality. And something about its energy has to do with how fast it oscillates, right? That's the photoelectric effect. Remember that we said that the energy content of a particle is about its frequency. And the frequency of a particle inside of a box, and this is true for all particles, the frequency of the wave corresponding to that particle is proportional to its energy. We're already starting to see things that we've seen before. Now they're just falling out of the math. Now here's the problem. I don't know what B and A are yet. Okay? We've just solved this very generically. So we need to figure out what A and B are. So we have to do what we have to, a classic example of differential equations. when you solve a differential equation, you get a nice solution, but then you have to apply the boundary conditions of your problem to get the right solution, right? We have to apply this to our box. So in order to determine A and B, we apply the box boundaries of our box. Okay, so now we have to think what the boundaries of our box are. I'm going to scroll back to my picture of my box again. And let's think about how the box is defined in terms of energy. The box says that the electron is free to be anywhere inside of the box, and the moment it hits one of the edges, right, if it's either on the wall at 0 or L or past it, the energy is infinite. Okay? So that means that the probability of finding the electron on the walls or past the walls is 0. Psi squared is 0 at these boundaries. All right, so this means that, let me go back to my previous page, is that because the energy is infinite, this means that psi squared at 0 is equal to psi at L squared, right? And these are both equal to 0, right? There's no probability of ever finding the particles on the walls because they're infinitely high. Okay? And this naturally gives us a boundary condition. We just take the square root of everything, right? So the boundary condition we have is that the wave function at 0 is 0, and the wave function at L is 0. Okay? So that's our first set of boundary conditions. Right? The wave function has to disappear when it hits the walls. It can't be past the walls, it can't be on the walls, so it has to be 0 at that point. So now let's take x equals 0 here and apply it into here. Okay, so let's look at the first one. Psi of 0 is A cosine 0 plus B sine 0. Okay, and this has to be equal to 0. Right? The wave function has to be 0, 0, so we have to just apply it. All right, so the cosine of 0 is 1. Sine of 0 is 0. Right, so we have A times 1 plus B times 0 is equal to 0. Right, so that means A has to be equal to 0. Right, there's no cosine component for this. Right, this has to be 0. Because, okay. So what that says now is that the wave function for the particle in our box here is just a pure sine. The cosine part goes away.
But why doesn't sine go away if sine of 0 is 0? I'm confused.
Okay, so psi of 0 has to be 0.
Mm-hmm.
So let's apply 0 into our general solution.
Mm-hmm.
We have A cosine of 0. You agree that's 1.
Mm-hmm.
So we have A times 1, A plus 0 equals 0. So we have A plus A equals A. There we have A plus 0 equals 0. That means A has to be 0.
Okay.
Okay? Cool. Does that make sense to everybody? What that means is that the function goes to 0 at the walls, which it should. Cosine does not. Remember, cosine at 0 is at 1. It's at its peak. So I'll show you. Let's just look at that. Actually, I think it's really good that we look at what this would look like. So let me draw my box real quick. So let's just take a perspective really quickly. So here's my box. I've drawn it with a top, but ignore that. And this is L and 0. Oops. I think it's better that we just look at it. And let's assume the function is a cosine. Okay, so what would that look like? Well, cosine of 0 is 1. So the wave function would look something like this inside the box. This would be a cosine. And what is the wave function outside of the box? It's 0. Right, so the wave function outside of the box in white is 0, and inside of the box it's a cosine. Is this function continuous and smooth? The answer is no, right? Because the limit as we approach this way is 1, and the limit we approach this way is 0. So the left-hand limit is different than the right-hand limit, so it's not a smooth function, right? They have to, the limits on both sides have to approach the same value. So this is discontinuous. So that's not a valid wave function, right? But let's do the sine. So this is not continuous. Right? If I were to just fill in the function, it would drop like this instantaneously at 0 and out, like that, right? It's not continuous. But if we have a sine wave, let me do it in green again. Right? A sine wave starts at 0 and goes up, goes down, and goes up, and goes down, something like that. That's a really poorly drawn one. And of course, the value of the wave function on the outside is 0. Right? So let's take the limit of the wave function as we go from the left to the right side of a boundary. Come here, 0. The limit as we go this way towards the boundary is 0, and the limit as we go this way towards the boundary is 0. So this is continuous. So in order to satisfy all the properties we need, the function has to be continuous. This is another reason why e to the x wouldn't work. Because e to the x at x equals 0 would be 1. It would be here. And then it grows like this. Right? So if it were e to the x, I'll just draw it. We'll just look at it. Right? And this immediately tells you why e to the x can't be a valid solution of this problem. All right, wrong color. Let me get a little bit more space. There we go. So if e to the x, same drawing, from x equals 0 to L for e to the x, e to the 0 is 1, and then it monotonically increases, right? But the wave function is still 0 on the outside, right? So this is very not continuous. Right? Not only is it not continuous on this side, it's going the wrong way on the other side. Right? This is e to the x. Right? So that's a really bad choice. Okay? So it does satisfy the differential equation, but it doesn't satisfy the property that the system must be continuous. So that means the only answer is sine. Okay, so I want to put a big fat check mark on this one, and an x on this one. Okay. Now here's the cool part. I think this is really amazing, and it's amazing how simple this works out. Yes, ma'am. Go ahead.
I have a question about the boundary of the...
Yes.
So sine is only 0 when sometimes, like on certain
Yes.
points. Is it just assume that the boundary is like far enough that it's always going to be 0?
Let's answer that question right now. The answer is no. But we haven't evaluated that boundary condition yet, right? So let's come back to it. You're right. So far, what we have, great question. Very prescient. Right? We have this. We have not evaluated one more boundary condition. We've only boundaried the one on the left side, right? We also have that psi is of L is equal to 0. Okay? So how do we satisfy this property with the function we have? Well, there's two options. Right? The only one way is to have b equals 0. Right? Well, then we don't have any function at all. Right now, the wave function is trivially negative, is 0. Right? This means no particle. Okay, so let's avoid that one. Right? So that's one way we can get this boundary condition satisfied as b equals 0. But we don't. That's worthless, right? We want to have a particle. We don't want to destroy it. So what's the other option? And this is what Anna's basically suggesting. Is that what are the other values that sine gives you a 0? Well, it's at integer multiples of pi, right? Sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. Sine of 3 pi is 0. Right, so you always have, so the other place where this is satisfied is when kx is equal to n pi, where n is an integer. Right, well, that gives us a solution for k. It says that k, so the thing that satisfies this boundary condition is when k is an integer multiple of pi over L. Right? There's an integer part of it. Right? So k can be pi over L, 2 pi over L, 3 pi over L, 4 pi over L, or whatever. Right? But it has to be equal to some integer multiple of pi over L. But now here's the cool thing. Is that I also define k. Remember, we wrote it down earlier. Right? It's proportional to the square root of energy. Right? So now we can relate these two formulae together. Right? We have something k is related to energy, but k is also related to this n number. So let's relate them. We have n pi over L, where n's an integer, is equal to the square root of 2me, the energy of the particle, divided by h bar. Okay, and let's solve this for energy, right? That's what we really care about. Remember, we're doing the Schrodinger equation. We want to find the energies of our system. So here's an equation we can solve for E. E is equal to, once we just do a little bit of math and some pi's, h squared n squared over 8 times the mass of the electron, L squared. And I'll write E sub n here. And of course, n is an integer. By assuming, now this is a big result, but by assuming that our wave function is a oscillatory function, right? That satisfies all the properties we want. And that it satisfies the boundary conditions that we want. That means that the frequencies of our wave have to be some integer multiple of pi over L. They can't be anywhere in between. They have to be pi over L, 2 pi over L, 3 pi over L, 4 pi over L in order to satisfy continuity of the wave function at the boundaries. So that immediately gives me an energy function that also is quantized, that also has discrete values. So what does this say? Well, it says that the energy of our electron in our box only takes specific values. It can be at 1 times this number, h squared over 8 MEL squared, right? That's just a constant. L is the length of the box. Right? So it's n squared times a number. And the energy of our system can only be at 1 or 4 times that number, or 9 times that number, or 16 times that number, and nothing else. Right? This is quantization, right? This is the sign. Just naturally, the idea that energy levels are quantized, right? That you see discrete lines in your spectra, right? When you do spectroscopy, you see discrete lines, which we described corresponded to discrete energy levels. The system can only exist at specific energies that are indexed. It just falls right out of the math right here. Right? That the energy can only take values that are proportional to n squared. Right? So this is quantization. So immediately, by just assuming a few things and satisfying the properties of our equation, satisfying the properties of the wave function, we naturally get quantum mechanics out, as you know. These are stick spectra. This is those stick spectra, atomic spectra that you saw that are all discrete lines, absorptions and emissions. Well, here's the source of it. Now, this is a slightly different problem than an atom, but in an atom, we're going to see the same thing. In an atom, we get a function that's 1 over n squared instead of n squared, but it's still this kind of structure. Right? So this idea of quantization, that energy can only take discrete values, or anything can take discrete values, naturally comes from the fact that our solution has wave-like properties. And in order to have a continuous wave that satisfies the physical boundaries of the system, you naturally get out quantization from it automatically. The idea is that each box has a note, a fundamental note. And the only notes that you can play inside of this box with your electron are harmonics of that note. You have n equals 1, that's kind of like your fundamental harmonic, or your fundamental note. And then you have harmonics above that, and they go as n squared. Right? You have the first harmonic, which is this value, and then, the fundamental, which is this value, and the first harmonic would be 4 times that value, and the second harmonic, or the third harmonic, however you want to look at it, 9 times that value. They're not equally spaced like notes are, right? Notes are spaced by octaves, which means they have equal spacings between them. Here they go as n squared. They're not equally spaced. But it's the same idea. You have the only notes that are allowed in this magic box are ones that are resonant with the box size, and those are quantized as n squared. Right? You have a fundamental, and then a first harmonic, then a second harmonic, and a third harmonic, and they're spaced in squares instead of linear, like acoustics are. You know, an A note, for instance, first harmonic of an A note is double the frequency, right? So that would be n linear, and then the next one's 3 times the frequency and 4 times the frequency. But here it goes as n squared in a box. But it's the same idea. We're going to see this time and time and time and time again, that the way that we treat quantum mechanical systems are like notes, and they have a pattern to their tuning, if you will, and the tuning is dependent on the size of the box and the mass of the electron. But there are fundamental notes and harmonics, and those are the allowed solutions of our problem. So, what do we have? So let's put this all together. We have 5 minutes left, which gives me just enough time to get us right where we need to be. We have that the wave function, we haven't solved this B term yet, but we will in a second. Has a form a sine of n pi x over L. And they have associated energies, h squared n squared over 8 times the mass L squared. Right? These are our particle in the box solutions. There are an infinite number of them. Remember, there is infinite energy in this box. The energy of the particle can be anything. Well, it can be infinitely large. It has to be quantized, but it can be infinitely high. N can go as high as you want. Right? So there are an infinite number of these, countably infinite. But every particle in the box has this solution and these energies. It's completely general and universal. And the only thing we have to determine is this B number. All right, so how are we going to figure out B? We have one more property to use, and I'm just going to finish this up in the last couple minutes. So let's determine B. All right, we're going to use the normalization condition that the integral over all space of our system, psi squared, dx is equal to 1. This gives us a constraint. All right, so let's do that. So we're going to integrate over our box. That's an integral from 0 to L of the square of our function, b squared sine squared n pi x over L dx. And that's going to be equal to 1. We know it has to be equal to 1. It's a normalized wave function. So if Calculus 2, you probably learned how to solve this, but you probably forgot how to do it, and that's okay. So let me solve this integral for you. We're going to do it by substitution. It's going to just take us 30 seconds. All right, so I'm going to let u equals n pi x over L, which means that du is equal to n pi over L dx. Okay. And this allows us to transform the integral. I'm going to factor out the b squared because it's just a number. This is the integral from 0 to n pi of sine squared u du. So again, this integral is really easy to tap. It's in tables. In fact, I'll show you next class. I have a really nice sheet on Canvas of really common integrals in this class. You just look them up and solve them. You don't have to do them yourself. But anyway, the way this works out is you get b squared L over n pi times n pi over 2. And that's equal to 1. All right? And so that means that we're just doing some algebra, some simplification, that b squared L over 2 is equal to 1, which equals, that means that b is equal to the square root of 2 over L. Okay? Simple as that. That's our normalization constant, right? So we multiply our sine wave by this function square root of 2 over L, and now our wave function squared always integrates to 1. Right? That's all we're solving here is the b that gives us an integral of 1 for our sine waves. It's 2 over L. Let me clean. Yeah. Super, super easy math. Again, I'll show you that on the beginning of next class. I'll show you that sheet on Canvas with all the integrals. Because we're going to be, as you may imagine, we're going to be doing a lot of sines and cosines in this class. Right? Our wave functions are sines and cosines in this case. We're going to be doing integrals and measurements of that, so we're going to have to think about trig integrals a lot. So let me just add that here at the top. B here, not just a number, it's not just some random number, but it's the square root of 2 over L. And this is a perfectly general solution. Right? If you have a box that has infinitely high walls, or at least effectively walls that are much higher than your energy of your particle, your wave function looks like a sine, looks exactly like this. It oscillates like a sine wave that has quantized frequencies and quantized energies that are of this formula here, where n is equal to, let me just write that here, n is equal to 1, 2, 3, dot, dot, dot. Now, one more comment before we go, just 10 seconds. Last thing I'm going to say. Notice that n has to be 1 here. So the lowest possible energy for the electron in a box is h squared over 8 MEL squared. That's a positive number. There is no zero energy electron in a box. Electron always has energy in a box. We're going to see this time and time again. That should be odd to you because you can imagine an electron that's just sitting there frozen, no energy at all. Okay, that would have no energy. E equals 0. But this is telling me the minimum energy has to be positive and non-zero. Right? We're going to find out that this is something extremely unique to quantum mechanics, and you can't get around it. That the electron always, in a box, always has some energy to it. You can't get rid of this energy. There's no lower energy state than n equals 1. There's no n equals 0. N equals 0 means there's no electron. There's always energy in the system. What you actually find out is because of this is the reason why absolute 0 is impossible. Because imagine if your universe was a bunch of electrons in a box, and you tried to cool them out as much as possible. They're always going to have this much energy, no matter what you do to them. The only way to remove that energy is to destroy the electron. That's why you can never get down to 0 Kelvin. Because you can never get rid of all the energy out of the system. You're always going to have some residual, which is the n equals 1 state of the system. All right? We'll characterize this more carefully this semester, but we're going to see this time and time again. That E equals 0 sometimes doesn't appear. That sometimes something always has energy. And this is the first time it comes up. All right, so we'll evaluate that and look at it tomorrow, next class. We'll draw some pretty pictures. We'll start measuring things on Thursday and have some fun with our boxes. All right, have a good one, everybody.
It still says assignment 0 is still not done.
I haven't updated it yet. Don't worry about it. I'll take care of it.
I'm teaching them the integrated ones today.